So this is going to be an explainer about KNN, which stands for K-Nearest Neighbour. It's a really simple supervised learning algorithm, really good to know, can be highly effective, can struggle if there's not enough data, but we'll go through all of that, but a really good starting point in terms of learning a bit about algorithms in machine learning. So in this, we're going to dive straight in, we're going to learn the concept, we'll walk through a toy example, and then we'll unpick the various aspects of what you need to know to essentially use it effectively in a library like sklearn. The example which follows this, so the walkthrough which follows this, will then give you a walkthrough example of what you actually need to know. So you don't need to actually be able to calculate all the equations that I'm going to write down. There's not actually that many, but you just need to know what the options are in terms of when you call that function in a library. So that's what we're really going to focus on. So first of all, we'll just do a quick recap on what we understand by supervised learning. I'm also going to talk about non-parametric. Sounds complicated, but a good term to know. And so why is KNN a non-parametric supervised learning algorithm? Okay, so just recapping wise, what we mean in machine learning when we say supervised learning is we have inputs, which we're going to call X. They go through a process, which is the process that we're seeking to learn. So the machine's trying to learn it. And then we have output values or target values, Y. This could be all sorts of things, like, loads of examples of this. But let's think of a concrete one. This could be a picture. So the input would be the pixels of the picture. And then the output might be, is it a cat? That classic question that you always ask yourself. Right, okay, so in supervised learning, what we end up having is we have labeled examples of this. And so what this will be is we'll have a whole set of X's. So in maths, little curly brackets means set. This is nothing more than just a bucket of examples. In the picture example, you could just think of it a folder on your computer where you have lots of labeled examples. So this would be X1, X2, all the way up to Xn. And associated with each of these inputs, there would be labels or target values which correspond to each of those inputs. Oh, wrong one. So this is Y, Y1, Y2, Y3. So to use our running example, X's would be pictures, Y's would be true or false, whether it was cat or not. So that's an example of a classification problem. We've been through this. So this means input to a label. But also, so KNN can do classification problems. They can also do regression problems, which is what we'll look at first. So where we go input to a number. So trying to think of an example on my head. If you, say, wanted to predict the relationship between a shop's, the time of day and the distance a shop was from the centre of town with the number of sales they made, this would be kind of a regression-based problem. You'd have two inputs. One would be time of day, one would be distance to town, and then the output value would be a number, maybe pounds or dollars, depending where you are in the world, about how many sales were done at that period. So examples, classification and regression can both be done with KNN, and so it's kind of useful in that way that you don't need extra methods if you've got different types of problems. Right, okay, so let's go to the basic principle. And so let's do this by a picture. So imagine we've got a data set, which is our X's. And let's take that last example where we've got time of day and distance from the centre of town. That's two inputs. So we can visually think of this, of each of the example data points, as dots on a graph. Get a bit of coverage, right? Okay, and each of these dots have associated labels y with them. And so now the question in K&N is I give you a new point, and so let's call this new point x tilde. So we haven't seen this data point before, and we're going to say, well, how do we predict the y, the value or label associated with this new unseen point? So what K&N does, the K basically stands for the number of nearest neighbours that you're going to include in that estimate. So if we said 4, what would we do here is we would ring fence the 4 nearest neighbours around our green dot. And then essentially we'd use the values of the target values of those 4 nearest neighbours to infer what our value at the green dot would be. So in this case, so if we labelled each of the points that are our nearest neighbours as, we're going to use hats. So we'll have x hat 1 with its value y1, x hat 2, and then we'll fly through these. So these are the pairs in our data set which are inputs and their associated value, their target variable output, that are the nearest neighbours. So these are associated with each of these points that live around this green dot. Now, the simplest prediction I can make is I can essentially average the values of those points. So y tilde, the prediction that's going to go with at my new unseen point, is simply going to be 1 over 4, because there's 4 points, but in general it's 1 over k, and I'll write that down in a minute, and it will be y1, y hat 1 plus y hat 2 plus y hat 3 plus y hat 4. And this is just a simple average of those points. I'm not going to go through it here, but there is a more sophisticated version which is a bit more complicated, not that more complicated, where you essentially, instead of doing just a simple all of equal weight, you essentially associate the contribution to the average proportionate to the distance it is from that new unseen point. So the logic here is that if the point in your training set is very, very close to the point you seek, you'd like that to have a greater influence on the prediction. And so to do that, you do a weighted average based on the distance rather than just a uniform average where everyone is equal. What you'll see when you have very large data sets and there's good coverage and relatively small values of k, then this doesn't actually vary much. But when you have more limited data, this is probably more important. When you implement it in scikit-learn, you have an option of choosing weighted or non-weighted average, and that's what this means. In general, by default, I would recommend you pick the weighted average because it will be more accurate with limited data. Okay, so here we're averaging because we're doing regression, right? So it makes sense that if our output variable is a number, so in my working example, sales, then we can average those values and we get a reasonable answer. If it's a label, true or false, a colour, or any other option, it doesn't really make sense to average them, because what's the average of cat, dog and cow? I'm not sure, right? So when we do classification, we need to think about how we do it, the assignment of our predicted value a bit more. But it's actually not too hard. So in classification, we don't do averaging, we do something called majority voting. So what this would ask in our context is we would have our 4 points and say that we're in the neighbour of our new point, and say one gave us true, which I'm going to call T, F, and that's to save me writing it out. So we're going to have one would be true, one would be false, one would be true, one would be true. So if these were the labels associated with the K-nearest neighbour, a majority vote would add up the trues, which would be, okay, trues equal 3, and there would be 1 false, false equals 1. And so in this case, the prediction would be the majority vote, which would be true. Okay, in cases which you might notice that if you take k to be an even number in the case that I'm looking at, you could easily get a situation where you had 2 trues, 2 falses. In this case, it doesn't actually matter which one you pick, as long as you pick it randomly. So 2 true and then false would be 2. So how do you pick this? So basically, when it's equal, if equal, you assign randomly. So assigning randomly means flipping a coin basically and saying, I don't mind. Okay. Right. So majority voting in the case of classification. So I mentioned when I was talking about regression that essentially you had this additional option of doing a weighted average. The same applies in classification, that if you have points which are closer to the predicted point you had and you want them to have more influence, you can give them more weight. And essentially that can be true in a voting setting as well. So you can apply the same method. When you use scikit-learn, that's again an option. So we've done the basic concept, and let's talk about the advantages and disadvantages of KNN. So what we really know is that it is a very simple algorithm, right? So it is very simple. Essentially, all you have to do is find the relative difference of your new point to all the other points, and then pick the k closest, and then do some averaging or some majority voting. So as long as your data set isn't huge, then sometimes it's worth trying as a first example on even for before going to something more complicated, because it might be good enough. The other good thing about it is it's identifiable. And what we mean by this is the fact that when you see more sophisticated machine learning algorithms like neural nets, once you've trained them, you're not really sure how they got to predicting their answer, and it can be very complicated. In this simple example and method, what it actually does is it does identifiability by example. So it says it is choosing to give you a result by averaging the values of these things that you've already seen, and you can identify them. So from this point of view, it's kind of simply identifiable by example. Okay, disadvantages. It can be very slow for very large data sets unless you do more sophisticated things. But essentially what you've got to find is distances from that point to the other points in the data set, and that can be a laborious task. There are sophisticated ways of calculating that which speed it up significantly, but still, you know, it's expensive relative to other methods if you have very large data sets. So slow for large data sets. Okay, and so the other part is that you need a lot of data. You are using, you are trying to look for examples which are close, and we'll get on to what close means. But if there isn't anything close, or you don't have an example in it because you just don't have enough example data, then you can imagine predictions will be pretty poor. So this is particularly the case when your input size is very, very large. So we were talking about pictures, for example, or pixels. To say one picture is close to another is quite a difficult concept. Like if you're looking just purely on pixel values, then close, you know, you need lots of examples to get close images to each other. And so this problem, as the input size or the complexity of the input comes higher, becomes even more the case. So let's get on to what do we mean by distance. And, you know, that might seem a bit of an odd question to ask because, you know, you can get a ruler out, you can measure the distance. But what I would say is that these aren't necessarily variables that a distance of a meter means anything about. Like how close is one picture to another is not as simple as just pixelated values. We won't get into it here, but when we describe distance in mathematics, people use the term as a metric. We decide a metric by which how close two things are. And often one of the big challenges in machine learning is this idea of metric learning. It's about understanding how we measure closeness of two objects. And so if it's physical distance, it's a really easy thing. And as I mentioned, for a picture or something more abstract, how close two pictures are is not a simple distance. Having said that, as a starter, in K-Nearest Neighbour, often simple ideas of distance are used. And so the conventional distance, which is Pythagoras distance or Euclidean distance, is often the traditional is often the first one that's used, and it's our traditional understanding of what distance means. So when we say distance, we want to know the distance between a new potential point and any of the samples, right? And so in Euclidean distance, we basically just use Pythagoras. So the distance between x tilde and some x will be equal to the sum of the square root of the sum from I equals 0 to m x tilde I minus xi squared. So what this does, let me write this out because I've used a sum notation. Let's unpack this. This is essentially Pythagoras. So this is the first component of the input squared plus the second component squared all the way up to the final component, which I've used m for. And then we square root the lot, right? So this is exactly Pythagoras distance. So let me try and do a little point. If this is x tilde, this is some xj, which we're looking at. We want to know this distance between the two. Then essentially we do let's call this d. We take this distance here, let's call it d1, and then we call this distance d2, and then the total d would be the square root of d1 squared plus d2 squared, right? And the distance here, exactly these measures here, right? Okay. So it's just Pythagoras, but it's in m dimensions. So we can draw it in 2, we can think of it in 3. In 4 it becomes a bit more of a strange concept, but it's just standard distance, and that's the basic one that's used all the time. There's also something called the Manhattan distance, so Manhattan, and so what we have here is we have dx tilde between dx, so the distance between the two is now just going to be the sum of the absolute values between the two. So in this case, we write this as x tilde I minus x j I. Ooh. And so writing this out, this will be x tilde 0 minus x tilde plus x tilde 1 minus x1 all the way up to x tilde m minus xm. Okay, and so in this case, we just take literally the differences between the values, and whether they're positive or negative, we make them positive. So this thing's just the absolute value, and then we just add them all up. It's just a different type of distance, slightly different in its behavior, but you know, a similar effect. There's not much difference between Euclidean distance and Manhattan distance. Okay, and then so the final one that I'm going to cover here, and there's lots of different ways of defining distance, so I don't want to hammer it home too much, and that kind of leads me into the Hamming distance, which means you might ask, well, what if the inputs themselves are labels? what does the distance between a cat and a dog mean? And so the simplest, when you have categorical variables for the inputs, the simplest one that you can do is essentially the Hamming distance. So we look at dx tilde and dx. Basically, we can assign it to be 0 if they're equal, or 1 otherwise. So a bit of notation here. This is like case notation. So this distance value gets assigned 2 values depending on the case. So if the labels are equal, so say this was a label cat and cat, then cat and cat are the same label, the distance between them would be 0. If alternatively it was cat and dog, the 2 labels aren't the same and we assign a distance 1. There are more complicated distance for categorical variables, but this is the easiest and standard one to use. So when we talk about distance, just to recap, that often in simple algorithms we need simple Euclidean distance. But in general, in more complicated machine learning, and there are examples that you can use in sklearn, that distance can mean a much more complicated thing. Okay, final part of this is how we choose k. So I said at the beginning that this was a non-parametric method. And I remember first thinking about this and thinking, well, this is odd. KNN's a non-parametric method, but the first thing you hear about it is k, and k is a parameter which determines how many variables or how many neighbours you average over or take majority vote from. And this sounded really weird to me. The point when we say non-parametric is it makes no underlying assumption about the distribution of your data. It just looks up for examples and makes inference from that. The k is considered a hyperparameter of the method itself and is a choice in how that method is used. So given a particular k, there is no underlying assumption about the data, and hence K-nearest neighbour is considered non-parametric. But getting back to that, how do we pick the hyperparameter, which is the k? And so the point is that if we choose really small values of k, we're going to depend on isolated points in our data. So small k means that we're going to have a bet that the closest one is the best value, right? So it's going to be dependent on only a few data points. And this means that you'll get a very localized prediction about what the response should be. Alternatively, if you take very large k, then essentially it will smooth the prediction. And so imagine if you included everything, every data set, so you had 100 data points and you choose k to be 100, and then you just take the average of all the nearest neighbours. Well, the data set is all the nearest neighbours, and so you would just return an average of the data set. So you would have no specialization associated with the particular value you're asking it. And so what we describe these two is small values of k lead to something called overfitting or overspecialization, and they don't particularly generalize well to unseen points. Large values of k basically just give you too smooth a response that you don't need, that you have poor predictions because you bias your model from limitations in how well it can specialize in localized regions. So what we really want to do is we want to ask the question, how well does it generalize to unseen points? And so in our machine learning workflow, and we'll get onto this in other parts of the course, imagine we've got our whole data set here. What we will do is we will keep some for training, and then we will keep some for testing. And this testing set will not be seen by the nearest neighbour algorithm at all. And then what we can do is we can try out, so what our aim is to do is to make a plot of k versus error in our testing set. So what we're going to call is error, EK. So the little k, so E stands for error, K denotes the value of K I'm predicting the error in, and then I'm going to sum up over my test set, and I'm going to look at the difference in the values and test, the number of points in my test set, the difference between my predicted values in this and my actual values that I've already got from my held out label set. And what you'll typically see is, so overfitting means high error to unseen data. So you'll see it overfitting up here. The error will come down and then you'll see underfitting overtaking. So we'll say this is overfitting. Oh, not overfitting. Underfitting. Underfitting. And this is overfitting. Okay, and then so the sweet spot is down here where the error is the lowest. And so typically we would try and choose a value of K, we'll call it K star, which leads to this minimum error. And this would be considered optimal, a balance between overfitting and underfitting. And you can only really tell this after you start testing your data. So the typical workflow is you would build multiple K-nearest neighbour models over your data set for different values of K. You would evaluate this held out data set that you've got to evaluate the testing error, and then you would selectively choose going forward the best choice that you've got by the lowest point on this graph. So in the example that's going to come through the walkthrough, we're going to go through an example of exactly how you do this. So you'll be able to put it into practice. If some of the maths is a bit confusing or the equations are a bit confusing, don't worry, because to actually implement it in Scikit-learn, you don't need to know those equations. I just want you to understand the concepts of what's happening behind the scenes. So in conclusion, so it's a supervised learning algorithm. So it's using labeled data and mapping, trying to learn the relationship from X to Y, and it does this by example. It is non-parametric, and we mean that we make no underlying assumptions about the distribution of the data that we're handling with. It's a nice method because it's simple and you can try it out quickly, providing that your data set is not too large and the dimension of your problem is not too high. Right? When it becomes complicated, like in a picture, that close, understanding what close is very complicated, and the number of pixels required to describe an image is very high, these methods will fall apart. But generally, you'll see that they're quite easy to implement, so worth a try. There are different ways that we can describe distance. So don't just think about the classic concept of distance, and we'll go through some of those in the walkthrough example, but generally, nearest neighbour uses standard distance that you understand, Pythagoras distance. And then there are methods for picking the value of K, and we use something called cross-validation. So we have this held out data set which allows us to evaluate different models for different values of the hyperparameter, which is K, so we can pick the optimal based on our test set value of K. Next steps, recap this, go through the maths, maybe try and write some of it out yourself. If you'd fancy trying to code an example yourself, you can do that. But in the walkthrough, we're going to show you how you can do this using a simple example in Scikit-learn.